Handful of questions from the homeworks. The one that's due this evening, we'll start with that, and then the one that's open, probably be due Friday evening. We'll do a handful of that as well. The first one here, I think this is question 20. Asked you to use the difference quotients we talked about yesterday with question 21. But this one incorporates a little bit different algebra as we progress through it. So we'll make sure that we understand that algebra, understand the processes, and why we do them the way we do them. So the first one, they ask you to find f of a. Obviously, I think that's pretty obvious. That's going to be 3 over a plus 6, right? Okay, so the idea here, and this is the same with all functions, whenever we evaluate functions, okay, that x is kind of like, if you remember back to like 7th grade or 6th grade, when you started first introduce algebraic concepts, they would put, instead of a variable there, they'd put like a box. They say, well, what can you put in that box? Okay, well, that's what the variable stands for, okay? And they're telling me, in this case, in that box, instead of x, you can put a. Okay? So that, I think, analogy helps me realize when I have to find f of a plus h, that's what goes in the box. A plus h goes in the box. So everything else stays the same. I have the 3, I have the plus 6, but now that box is going to turn into a plus h. Does that make sense? Okay, I've had several people come to me and not understand, what is it I'm substituting in for these variables? Do I put just a? Do I put a plus h? What do I do? Okay, that variable is giving you a location to substitute whatever they tell you to. Okay, and if I see x several times, then I've got to put that in several times. I got to fill that box multiple times if that's the case. The last part then asks us to actually find that. Take f of a plus h minus f of a and divide by h. Okay, so what that's going to look like is 3 over a plus h plus 6 minus 3 over a plus 6. Okay, now that is just that so far, correct? I then need to divide by h. Okay, now I'm not sure what WebAssign is going to do. If you type that in, my initial guess is that's going to count wrong. I'll tell you you're not simplifying. Okay, so we want to go through and simplify this. Now we've got a fraction divided by a fraction. Would you guys agree with that? Okay, so this h over 1 is a fraction. Now, in order to address this kind of the most efficient manner, I want to deal with that top difference first. Because remember, and you learned this in Algebra 1, you should have learned this in Algebra 1, that when we have division of multiple terms, okay, that division bar behaves like parentheses do. And it's going to group the top, and it's going to group the bottom. So what we want to do is deal with that top first. And I want to actually combine that into one fraction. If I'm going to divide a fraction by a fraction, it makes sense for that top one to be an individual fraction. So if I'm going to combine those, what do I need? Common denominator. And that common denominator is going to be a plus h plus 6 times a plus 6, right? So I need to multiply this left-hand side by a plus 6 over a plus 6. And this one I need to multiply by a plus h plus 6 over a plus h plus 6. And if I do that correctly, I should get 3a plus 18. That's when I multiply this one over here. Okay. This one, along with the negative that needs to be distributed, should be negative 3a minus 3h minus 18. And now the purpose of creating a common denominator was so I could write this as a plus 6 over a plus h plus 6. Then all of that, so that line right there is that red division, right? And then I should have this over h over 1. Okay? Now, if you're doing this stuff correctly, if you're using this, what they're calling the difference quotient correctly, you should generate some cancellations. Do you agree that 3a and negative 3a cancel? Positive 18 and negative 18 cancel, right? So all I'm left with there, if I've done things correctly, is a negative 3h over the a plus 6, a plus h plus 6, all over h over 1. So now it's still the original problem, but it's simplified. Right now it's a fraction divided by a fraction. Now I can use that process of multiplying by a reciprocal, correct? All right, now the reason that multiplying by a reciprocal works is because I'm going to do it to the bottom and I'm going to do it to the top, right? So I've really multiplied by just 1 over h divided by 1 over h, right? Down here, it gives me 1. Up here, what are these h's going to do? They're going to cancel. And I'm left with then negative 3 over a plus 6, a plus h plus 6. That's my final answer. If you want to distribute that bottom, that's fine. Okay? But generally, when we have solutions that have a denominator, you usually want to leave those factored. For the mere fact of our goal later on will be to find domains, and it will be to find particular places that provide asymptotes graphically, which is directly related to domains. In order to find those, you need the bottom factor. So it doesn't make a lot of sense ever to kind of FOIL that bottom out. So if you remember what that gave us yesterday, okay? So I want to kind of open our eyes to where we're going to be using this later on. If we have negative 3 over a plus 6, a plus h plus 6. Remember that h is the distance between 2 points on a secant line of our curve. Well, in order to approximate our slope, our hope is that that h gets very, very small, right? Approaches 0. So let's just wipe that away. Let's make that 0. And wouldn't that leave me negative 3 over a plus 6 squared? Does that make sense? Okay. Now, I want that a value, that is an x value. Okay, so what I'm going to do, I've graphed this already for us. Okay. This is the graph that we started with. And that process that we just went through is going to generate us a slope of this curve no matter where a is. Would you guys agree that if you were, so your feet have to be touching the curve, flat on the curve. Would you agree that if you were on this curve right there, you would experience, so my feet have to be flat, so that'd be my face, okay, I would experience a very steep slope here in comparison to if I was standing there, in comparison to if I was standing there. Does that make sense? Okay. So the slope is different as we move along this curve. What we just found should allow me to find that slope very quickly an endless amount of times. Okay? So the tangent line should look like that. So the slope of that black line, let's make it blue to talk about it easier. That's the tangent line. The blue line is the tangent line. The slope right here is negative 19.38. Well, what we just found was 3 divided by an x value plus 6 squared. Okay? Now that x value, I want that to be the x value of this point A. Okay? Because that's where I want to find the slope at. Does that make sense? If I hit enter, that's the number that just generated. Is that the same as that slope? Okay, now obviously it's negative, okay? But that slope, those numbers match up. Okay, and I think I actually need a negative here, right? So that was -3. All right, so those slopes should match up. As I move this point, and now I look at that blue line right there, its slope is -2.23. Does that formula, when I plug in whatever this x value is here between, or -4.84, I plug in that x value, I get that slope of that blue line, right? Does that make sense? So the slope of that blue line is the slope of that curve at that point. So what ends up being nice is I don't really need the blue line anymore. If I want to know the slope of that curve at A, it's -0.52. If I want to know the slope at A right there, it's -2.52. Does that make sense, everybody? So that it creates a formula, the difference quotient creates a formula that allows us to find that varying slope anywhere that I want to. Okay? Which is nice, because on lines, we've always talked about, well, once you find the slope of a line, it's always that, right? It's constant. Well, with curves, it changes instantaneously. Every single position, it's different. Okay? Well, I would not want to, because we're going to be very interested in these slopes eventually. I would not want to go through the process of finding the slope at every single A point by hand. I would rather have a much quicker approach, and this is the quicker approach. Okay. In disregard to the calculus aspect, are we comfortable with this algebra? Okay. Combining like terms and that kind of stuff. So yesterday we spent about 15 minutes on this question. Today we spent about 15 minutes on this question. Okay. So it's a good half hour on that question. So if we're taking that much time in class, it's probably something we should probably know, right? Okay. I've got 3 domain questions here I want to target. Put them in the order that I want to go through them. So write that one down. We're going to figure out the domain of these. 2 of them shouldn't be too bad. This domain is comparable to the 6 that we did yesterday. And the third one that we do isn't all that bad either, but it does add a little bit of a twist. All right, so remember, these are our 2 restrictions. These are our 2 places that algebraically give us issues. Okay? Division by 0 and even roots of negative numbers. Okay? So, in this problem, do I have division? Yes, so I have a potential for division by 0. Okay, so I got to be cautious of that. Do I also, in this problem, have the potential for taking roots of negative numbers? Yeah. Okay. Now, in this situation, those 2 things happen kind of in the same term, right? Does that make sense? So
does the numerator never like that?
So yes, so in this case the numerator doesn't matter, because if I think about any number that I want to plug into the numerator, you add 9 to it and then square that number. Yeah. So ultimately what we're looking at, ultimately what we're trying to do here is, if I've got this x plus 9 squared over root 6x minus 1, what we want is we want to plug a number into that x and get a real number back. And we're going to plug a number into that x and get a real number back, because we know that a real number divided by a real number ends up giving me a real number, right? So I would get an output for that function. Okay? Think about this though. If I have any value x up here that you can think of, add 9 to it and you can square it, right? Okay? Try a negative number, try negative 12. I don't know where everything's disappearing. Try something like negative 12. You would get negative 3. You would square that, and it'll give you a real number back, right? If I try 0, I get 9. Square that, 81, get back. I try a positive number, 12 plus, let's go 11 plus 9 would be 20. Square that, I get 400. That's a real number back, right? So kind of all my positions, I get a real number back. Down here, though, if I try, let's try 10. I get the square root of 59. Well, that's a real number. So a real number divided by a real number, that'll give me an output. But if I try something like, let's say 1/6. If I try 1/6, what do I get back? I get 0, right? Now that's a real number, but am I allowed to do division by 0? So that wouldn't give me an output, right? So I got to make note of that. Try a number like negative 10. It give me negative 61, and that would give me I radical 61 underneath or in the denominator. Can I divide? Is that a real number? No. Okay. So a real number divided by, in this case, an imaginary number is not going to give me a real number. So it's not going to give me an output. So the procedures that we go through, guys, are going to quickly narrow those situations down for us. Okay. Instead of having to think about them logically like that, because that can be time consuming. You have to think a little bit different every single problem you come across. These procedures will determine that instantaneously for us. Okay, so what we do, like Blaise said, the numerator doesn't matter because it's a polynomial essentially. But the denominator is a problem, and the denominator has two problems here. Our denominator is 6x minus 1. That has to be, with any radical, we have to say it's greater than or equal to 0, right? You can take the square root of a negative. Or sorry. You cannot take the square root of a negative, which means you can take the square root of 0 or anything that's positive, right? So we're looking at square roots of non-negative numbers. If I do this, I'm going to be wrong. Why would this be wrong for this particular problem? Because it can't be 0, because it's in the denominator, right? So this is one of those. It's a little bit of a twist to it because we're used to saying radicals, and I just say greater than or equal to 0. So because the radical's in the denominator, it's just greater than 0. And now we solve it. X is greater than 1/6. Okay? And there are no other restrictions. Okay? Nothing, because the numerator was fine. The numerator had no problems with it. That is the only restriction, only condition that we come up with. So then we have to write that in interval notation. So 1/6 to infinity. We haven't talked about what this kind of graph looks like. Okay? And to be honest with you, we may never even talk about this type of graph. Okay, it's a rational graph that incorporates a function or a square root function.
Mr. Wilkerson's students, this is just a reminder to let you know Mr. Wilkerson has returned to the building. So Mr. Wilkerson's classes are to report to his classroom as regularly scheduled, starting next period. Thank you. Or beginning with his Wildcat time. Thank you.
Okay, so we're looking at this curve here. Oh, I froze it. We're looking at this curve here. Okay. Now, if I look at this, okay, 1/6. I've put the line x equals 1/6 in here. That blue line. That brown curve, or whatever color it is, will never get to the left of that blue line. Does that make sense to everybody? Okay. And that's exactly what this domain here is telling us. All right. Questions on that? All right, let's try this one. What's important about this one though is that, and we need to start thinking this way, is, multiplication to you guys is an inherent skill. You understand how to do it, right? Yeah. We know how to multiply, we know how to divide, we know our operations. Those are prerequisite skills that are just common knowledge to us now, okay? And whenever we come across a problem that incorporates multiplication, we know how to do it, and we do it. At this point in mathematics, and whether this is fair and realistic or not, the idea is that you have witnessed, you have been exposed to factoring. So whenever factoring pops up in a question, you should be able to know how to adequately address that. And what's going to happen eventually is that question 1 will have factor by the AC method. Question 2 might have an intermediate step that has to factor by the quadratic formula. Question 3 might have a factoring by the rational root theorem later on. Okay? When you get to calculus, every question will incorporate some type of factoring probably, and it is going to be kind of like multiplication is. Okay? No matter what two numbers, however big I give them to you, you should be able to multiply them, right? So their argument then is eventually, no matter what I give you, you should be able to factor. Okay? And this is one of those situations. And that's how mathematics kind of plays out as you move on. Okay? Once you've learned the concept, they assume that you have learned it, you've mastered it to move on. So then when we show that as an intermediate step in another question, you should be able to use it. Okay? Does that make sense? Now what sucks about that is if you haven't learned that, you haven't mastered it, you didn't think it was a priority, the new information is not going to be learned, right? And then a month down the road when what was the new information now also becomes a intermediate step in another concept, that new concept, the third one, you're not going to learn, right? Does that make sense? So it starts to snowball real fast. All right, so here we got find the domain of this function. So we've got now a numerator that's posing a problem, right? Okay, and we've also got a denominator that is posing a problem. Okay, so the numerator, all I have to do is take the radicand, and now I can use equality. I can use equal to 0, right? Because you can take 0 and divide it by any number that you want to. So we have to meet that condition. Our number line has to be greater than or equal to 0. Regardless of what the green says, this has to be met. Okay? Now I'm going to do what the green says. And this is where I was getting at. We have to be able to factor this. How do I factor that? 9 times negative 1 gives me negative 9. And that's going to give me negative 1 and positive 9, right? So we're using the A times C method. So I'm going to rewrite this as 9x squared plus 9x minus 1x minus 1 equals 0. I'll group the first two, group the back two. What's going to come out of the first two? 9x. Leaves me with x plus 1. What comes out of the back two? Negative 1. Leaves me with x plus 1. So it's going to mean 9x minus 1 and x plus 1. And that's going to lead me to x to be 1/9 and x to be negative 1, right? Okay. Now, remember what we're really doing here. And I set them up as equations, but aren't we really trying to figure out what x is not allowed to be? X is not allowed to be 1/9. X is not allowed to be negative 1. Not allowed to be 0. Not allowed to be 0. Not allowed to be 0. And not allowed to be 0. Whether you actually do that and write those not equal to's in your problem, that's up to you. Well, that process is getting us that result of what we're not allowed to substitute into the bottom. Okay? So, it would be nice for us to realize that, well, x has to be greater than or equal to 0. X has got to be greater than or equal to 0. And x at the same time cannot be negative 1. And x cannot be 1/9. Okay, well, we have to write that as an interval. Okay, and the real thing here, I should probably put parentheses around. It's not a big deal, but this was from the denominator. This was from the numerator, right? In order to get a real number divided by a real number, both these conditions need to be met. So x has to be greater than or equal to 0. Well, if x is greater than or equal to 0, we're talking now about that number line, right? Okay. Is this number even in there?
Nope.
No. So does it matter?
Nope.
No. Okay. That would have been out here at -1 somewhere. It doesn't meet the condition of being greater than or equal to 0. We need to have both things. Is this number greater than 0? So what I need here at 1/9 is an open dot. So then to write my interval, we're going to start at 0, go up to 1/9, kick out 1/9, and go all the way up to infinity. And now what that does, that gives me a list of numbers. No matter what I choose out of there, I am guaranteed to get a real number in the numerator, and I'm guaranteed to get a real number out of the denominator, and a real number divided by a real number. The real numbers are closed under division, so we would get a real number back. Okay. Is that all right? Where to put the other one at? There it is. A little bit difficult here, a little bit more difficult. Shouldn't be something we can't do after maybe the first time we talk through this process with this understanding. What numbers are we not allowed to use? What numbers can you not take the square root of? Negative numbers, right? So I need to make sure that x squared minus 3x minus 10 ends up being a positive 0, or positive number, or 0. Okay? Sometimes when we say this phrase, it's easier to say non-negative. 0 or positive would be non-negative, right? Okay, have you guys ever dealt with quadratic inequalities?
Yeah.
You have?
Oh, those numbers.
I would venture to say that it's probably unlikely that you have.
Did you say quantum theory?
Quadratic inequalities.
Oh, never mind.
All right, so inequalities that we've dealt with are linear, and we solve them like equations, right? This you can't solve like an equation. Okay, this you have to have a different approach. Basically what's going on here is that we want to first find out where this thing is equal to 0. Okay, so in that respect, it is maybe a little bit like solving a quadratic equation. I'm going to factor this to x minus 5 and x plus 2. Okay, and now here's the thing. That's going to give me 2 zeros, right? That's going to give me the 0 of 5 and the 0 of negative 2, right? Okay. Now, I wrote it that way because it's weird with putting the inequality sign in there. I don't want to say x is greater than 5 and x is greater than negative 2 because that doesn't say what I really needed to say. But I find the zeros. What we're trying to do here, guys, is that we're plugging an x value in for the x squared and for the minus 3x, right? And we're going to evaluate that. And we want the left-hand side to turn into a positive number, right? We want to choose x values that will generate positive numbers on the left-hand side of this equation, or this inequality. Well, if I plug in 5 or negative 2, doesn't that generate 0?
Yeah.
So it shows me where they're equal. So now that I know where they're equal, I should be able to intelligently think about where they're unequal and in how they're unequal. Okay, which one is producing the greater than values or which one is producing the less than values. And you can do this with a quick sketch. You can maybe even keep track of this stuff mentally. But I'm going to just graph a quick sketch of this thing. We know that the zeros are 5 and negative 2. This is a positive 1x squared, right? So is this parabola concave up or concave down?
Concave. Concave down. It's a concave up.
You said up?
I said up the first time.
All right, so it is concave up. So would you guys agree that anything that is x squared, positive x squared, is going to look something like that? These zeros were where it's equal. The blue portions, would you agree that those are y values that are ultimately that stuff there that are bigger than or equal to 0?
Yeah.
Okay? And then this stuff here would be where we're negative, right? Does that make sense? Okay. If I understand that, and I understand that what this is generating is y values off this parabola, and I want those y values to be positive, then the y values are positive from negative infinity to negative 2, including negative 2, because I can be 0, union then 5 to infinity. Those are the only values for x that I can plug in that will generate then y values, or we evaluate the x squared minus 3x minus 10 to be a positive number. If I choose anything outside there, so anything outside there would be numbers like 0, right? 0 it's been kicked out. If I plug 0 in, don't I get negative 10? Is negative 10 greater than or equal to 0? No, that's why I can't choose it. That's why 0 does not show up as part of my domain. Okay? Now, with most of our functions that are polynomial, you can probably draw a graph and make that argument, make that assumption. Okay? But I would also argue that right now, our knowledge about cubics and quartics and quintics is maybe lacking, and that's because you haven't seen that stuff yet, or dealt with it a lot. So there's another way of doing this. There's a systematic procedural way that actually generates the same logic. Okay? So I want to teach you how to do that because it's become something that's very important through the rest of this course. Eventually in the chapters 4 and 5, and we get the trig, we'll do a little bit of this as well. And this is on the final. They ask you to write one of these on the final. So I want to make sure that we have capacity to do this. And what we're going to create is something we call a sign chart. A sign chart or a sign, sometimes called table. But basically all you do is you draw a number line. Okay? And that number line models the x-axis. Okay, basically this procedure, guys, is going to give us the graph that I have over to the left, the parabola, but in a more kind of a cryptic way. It's a little bit more or less detailed. Let's say it's less detailed. It doesn't have, we don't incorporate the y-axis here. Okay. But that there is going to model the x-axis. So if it's modeling the x-axis, the thing that we're going to want to do is once we factor this, we want to put our zeros on here. Okay, so I want to put negative 2 on here. I want to put 5 on here. Okay. And however many zeros you have, we'll talk about this later on in another example. If I have 3 or 4 or 5 zeros, I put them all up there. Okay. The next thing you do is that you come to the side, okay, and you create a column here of your factors. So one of our factors was x minus 5. The other one was x plus 2, right? And you're going to write all your factors that you have. So you might have 3, 4, 5, you might have 12 of them, whatever. You write them all down, okay? Once you've written them all down, the last thing you write, I always write total, okay? Some people will actually write what the actual x squared minus 3x minus 10 was, what the function looked like. Some people write p of x or f of x. I just write total, okay? Okay, so we got a number. So now, what happens, and kind of think about this, didn't these zeros over here kind of chunk our number line up and be or provide us the spots in which we were either above or below the x-axis? So I'm going to kind of come over here and I'm going to do the same thing. I'm going to say that my zeros are going to be places where I could potentially change position in relation to the x-axis. I could either be above the x-axis or below the x-axis in those regions. Does that make sense? But the change is going to occur at -2 and 5, or potentially occur at -2 and 5. Okay? Because that's where we will equal to the x-axis, or equal to 0. All right, so now you're going to do substitution. You're going to pick a number over here. Give me a number over here to the left of -2, and I don't care what it is. -7? Okay. So I'm going to take -7. I'm going to plug it in here. What's -7 minus 5? -12? What's -7 plus 2? -5. What's -12 times -5? 60. And it's positive, right? Okay. Now, here's the thing. Blaze had us choose -7. You might have chosen -10. Somebody else might have chosen -100. Okay? Any number that is negative, x, like to the left of -2, is x minus 5 going to be a negative amount? Choose any number to the left of -2. Is x minus 5 going to be negative? Yeah. Okay. Is x plus 2 going to be negative? Yes. If I multiply those together, and why am I multiplying those together? Because that's what we're supposed to do from that right there, right? Okay. Whenever I take a negative times a negative, we'll always get a positive. Okay. So even though in this situation I wrote down these numerical values, I don't really care what they were. I just care about the signs that they were. Because now what that tells me is that to the left of -2, to the left of -2, my graph should be generating y values that are positive. And is that what happens in our parabola? Okay. Let's try something between -2 and 5. What is a nice number in here to substitute between -2 and 5? What's a real? If I could choose to substitute something, I would always want to substitute what? 0. Okay, now you can choose 1 or -1 or 3, 4, whatever you want to, but if 0 is available, use 0. What's 0 minus 5? Negative, right? So any number in between -2 and 5 that I chose, or I subtract 5 from it, it's still going to give me a negative. What's 0 plus 2? Positive, right? What's a negative times a positive? A negative. Does that model what we were looking at in our graph over here, that between -2 to 5, you were below the x-axis? Okay. Then I come over here. Let's choose a number. Give me a number over here. Okay, 7. I'm going to say 7,000. I choose really big numbers because it makes the math almost trivial. If I have 7,000 subtract 5, that's really easy. It's going to be positive, right? 7,000 add 2, well, it's positive. That's really easy. What's a positive times a positive? Positive. Okay. Does that model then what we had right here? To the right of 5, we get positive solution. So what we do next to generate our answer that mimics what's going on here in this parabola picture is that we look at this total row. And we try to remind ourselves, what were we looking for? We were looking for things that were greater than 0. Things that were greater than 0. So is that positive numbers or negative numbers? Positive numbers. So when I look at positive numbers are being generated from there to there and from there to there. Does that make sense? And now if I were to put this red graph in interval notation, isn't it negative infinity up to -2? And I put this red graph into interval notation, isn't it 5 to infinity? Okay, so that's the procedure for making a sign chart. Okay, we will use that a lot as we move on through the next couple chapters. I want to do one more with you. The task of these guys is to always factor first. You have to factor in order to find your zeros, and then in order to write these down here. I'm going to do one with you, which just to save time, I've already factored it for you. So let's start with f of x is equal to the square root of x minus 5, x minus 1, x plus 4. So it's already been factored. Okay? If you FOIL that out, you'll see it's a cubic. Okay? It's a third degree polynomial. Okay? If we graph this, okay, what's going to happen? And the reason I want to graph these guys is just to prove to you that what we do sign chart wise is mimicking this graph here. Would you guys agree we'd have a 0 at 5? Would you agree we have a 0 at 1? And we'd have a 0 at negative 4, right? Okay. Now this way, if I were to FOIL this out, this would be a positive 1x cubed. And I know, and I'll teach you to learn this as well, that a cubic, if it's positive, the end behavior is going to look like that. And now to be able to go through these other intercepts, it's going to have to do something like that. Does it make sense? So my goal here then is to figure out, well, where is this? Because we want it greater than or equal to 0, right? We're going to be looking for a procedure in our sign chart that generates those solutions. So our answers for our domain should be negative 4 to 1 and then 5 to infinity. But let's see if our sign chart generates that. Okay? You create your number line. We put our zeros on it, negative 4. Positive 1, positive 5. You come down to the side. Okay, remember we were looking for this amount to be greater than or equal to 0. So we come to the side, we write those factors down. X minus 5, x minus 1, x plus 4. And then I need a total line, total row. Okay. Putting those dotted lines in there are analogous to the dotted lines right there where behavior changes at my x-intercepts. To the left of an x-intercept, I'm either above or below the x-axis, and to the right of it, I'm either above or below it. So there's a change in behavior there. So the sign chart allows us to recognize that change in behavior. So I choose a number. And like I said, I like to choose really big numbers when I can. So I choose negative 1,000. We'll subtract 5 from it, you get a negative 1,000. Okay, subtract 5 from it, you get a negative 1,000, right? So I'm just doing just really rough estimates here. But if I have negative $1,000 to somebody and I borrow $5 from somebody, it's not a big deal, right? In comparison to the total. So it's a negative, a negative. This would be a negative, right? So what's my total here going to be? Yeah, 3 negatives multiplied together give me a negative. What's a good number to choose here? 0, right? If I choose good numbers, this process of evaluating should be really quick. So choose 0, that's a negative, a positive. What's my total going to be then? If I have 2 negatives multiplied together, don't they turn into a positive? And then a positive times a positive.
Positive.
So positive. This one here, going to have to do some evaluating. So maybe I choose like 3. 3 minus 5, negative. 3 minus 1, positive. 3 plus 4, positive. Total is negative. Choose 1,000. Are these all positive? Total's positive. So my total line then, remember what we're looking for. We're looking for greater than 0, right? So where are greater than zeros? It's where we see a positive amount, right? That means the y values were greater than 0. Do you agree that it's between negative 4 and 1 and it's to the right of 5? So negative 4 to 1, I'll write that interval. Union then 5 to infinity. And those then would be the values that I'm allowed to put in my domain. And I want to graph this thing real quick for you, because you've probably never seen a graph like this. All right, so when we graph it, this is the graph. Okay? It looks nothing. Okay, it looks nothing like this little graph that I showed you earlier, right? When we started this problem. Where'd it go? It doesn't look like that cubic right there. Okay? The red part maybe does. But, okay, do we see that we have an interval from -4 to 1? And then from 5 to infinity? Does that make sense to everybody? That's the thing about mathematics that I want us to try to understand, is that our knowledge about quadratics, our knowledge about cubics, okay, and those interrelationships that exist between those things, and our fundamental understanding of this graph here, okay, can allow us to generate a procedure, okay, and our understanding of this then kind of validates that this procedure will work. Does that make sense to everybody? Okay. I think too often we get into a math class and we're shown how to do something, show you how to make that chart, but we don't draw the connections between what is allowing that chart to be made, what is allowing it to work, and us to gain those conclusions from it. Okay. And I think that's the part of mathematics that we need to gain out of this class, not so much being able to do procedures. Okay. Keep working on those homework assignments. The one is due tonight, part 1. The other one will be due Friday.